Okay. Yeah, just shut the door when you come in so that it's nice and quiet. You can see we're getting to the end of the course. Yeah, everyone's getting a bit tired. So next week, advanced and normal will be split. You just got a bit different material to each other. The advanced has got just a little bit more material. So this is the last topic that we're going to start. It's magnetism. And it's a very important topic in condensed matter physics. As you probably know, it's involved in many technological applications. Some of them are just sketched here. This one's a particularly nice example. It was designed purely on the basis of theory, and it's a superlattice material, and it exhibits giant magneto resistance, which means that when the spins are aligned in these different layers, you can see this is two different materials, and just looking at one layer here, and it's stacked up. You can grow it that way. As you know, the techniques are really well developed now. You can actually have that much sort of atomic control of where you put your atoms. And so that when the spins in these two materials are aligned together, you get a very high resistance, but you can apply a magnetic field and switch the spins the opposite way in these materials, and then you'll get a much lower resistance. Okay? So that's a very nice example, an important discovery, and so important that it got the Nobel Prize, I think, in 2007. Okay, so what we're going to look at in this lecture, we're going to really start with just single atoms and look at how their magnetism arises, and then we are going to consider the atoms in a magnetic field and in a solid later on. Okay? And as you'll know, most of the magnetic phenomena that we observe in materials is due to the quantum mechanical nature of what the electrons are doing. It's worthwhile mentioning that clearly all the magnetic phenomena cannot be understood just on the basis of the atoms. Noble metal solids, that's fine because they behave very much, they don't interact very much with their neighbours. But you know, when we have ferromagnetism, all the spins need to be aligned within a domain, and so these spins need to interact and talk to each other. But as I said before, we're just starting with single atoms, looking at single atoms. The nuclei also have magnetic moments and do contribute a bit to the magnetism, but as I've put here, this effect is an order of 1,000 less than that due to the electrons. So we are not going to go into that here. This is just reminding you of some of the fundamental equations that we have. Okay, we have, if you have a material in a magnetic field, remember these equations here, you will have an induced magnetization M inside the solid due to the spins aligning. I think these will all be well known to you right up from first year. We have the magnetization is equal to the susceptibility, which is a property of that particular material, times the applied magnetic field here. And we end up defining a relative susceptibility being equal to 1 plus the susceptibility here multiplied by mu b, the Bohr magneton. Okay, so I think that's probably you know, pretty well in your mind, and it's probably been in the courses that you've had before. And here are some of the units that you'll also remember probably. You know, we have B is in Tesla, and mu b has these units here, and so on. Just to remind you, a field of 1 Tesla is really strong, and compare that to the Earth's magnetic field, which is of the order of 10 to the minus 5 Tesla. Now, if you have one dipole and you put that into an external field, we have that the potential energy of that magnetic moment is equal to mu dot product with B. Okay? So overall, let's just get a sort of overall picture here. If we think of materials, we can divide them into sort of three categories. Okay? We have diamagnetic materials, and in this case, the magnetic susceptibility is negative, and so the magnetization opposes that of the electric field, magnetic field. So that's its main characteristic. It's negative, and it has a very small magnitude of about minus 10 to the minus 6 to 10 to the minus 5. Okay? And some examples of that are ionic crystals or inert gases. Then we have paramagnetic materials, where again the susceptibility is positive. And so we have that the magnetization is parallel to H, and it's also fairly small, of the order of 10 to the minus 4 to 10 to the minus 5. Then we have the probably more well-known kinds of magnetism, ferromagnets, where we have the susceptibility is really large, of the order 10 to the 5. Okay, so this is when you get this spontaneous magnetization. You don't need a magnetic field to induce the magnetism in these materials. Then there's also, have antiferromagnetism. Ferromagnets, all the spins are aligned in the same direction, and antiferromagnetic materials, they are completely anti-aligned, if you like, and the net magnetization is then zero. We'll talk about that a little bit later on. And then you have ferrimagnetism, where you have some spins are aligned and some are anti-parallel, if you like, but the net magnetization is non-zero. For the diamagnetism, we have the expression here for the potential energy. You can see it's equal to volume, V, susceptibility over 2 mu 0 times the magnetic field squared. You don't need to know how to derive that. If you're interested, you can look in Ashcroft-Mermin, but you're not expected to know how to derive that. And sort of the mechanism for diamagnetism is a bit like Lenz's law. If you think about an atom, nucleus, and you've got an electron going around, in a magnetic field, then this electron will induce, you can think of it like a current going around, and that will create a magnetic field, and that magnetic field is created in a direction that opposes the applied magnetic field. Okay, so you will all be familiar with Lenz's law, so you can think of it like that for diamagnetism. For paramagnetism, you can think about it, you've got an atom, and some of the electrons will be unpaired. Okay, so you won't always have a spin up and a spin down to get zero magnetization. There'll be some electrons that just have a spin, and when you apply magnetic field to those materials with those kind of atoms, then all the spins on the atoms will tend to align with the magnetic field. But if you don't apply a magnetic field, those spins will just be randomly orientated. Okay, this just explains a little bit more what I sort of said verbally. If you can think of ferromagnet as being one where all the spins are aligned, some examples are iron, cobalt, and nickel. And antiferromagnetic material, you have, there is a magnetization, but in the opposite direction to each other, and the spins perfectly cancel. Okay, so you get a net magnetization of zero. And the ferrimagnetic, you have some regions or some atoms spin up and some spin down. Okay, and the net magnetization is non-zero. An example of that is magnetite. and for antiferromagnetic nickel oxide. Okay, as I mentioned before, ferromagnetism, the most common ones from the periodic table are iron, cobalt, nickel. There are some other ones involving rare earth elements, gadolinium, and this one I've even forgotten how to say that one, and transition metal oxides, chromium dioxide. Okay, the magnetism in these materials arise due to the unfilled 3d electrons, for example in the iron, cobalt and nickel, and for the rare earth elements in the F shell. Okay. Another thing about ferromagnetism, as a function of temperature, if you heat up the crystal beyond a so-called Curie temperature, then you will lose that magnetization and you won't get you won't have a magnetic material anymore. Okay, so that's called the Curie temperature. Okay, so this I put here to show you what the d-electronic states look like, or orbitals. Sometimes they're called states, coming more from physics. Coming from chemistry, they usually call them orbitals. And these are the 5 d orbitals. So if you have an atom there in the center, these are the way the lobes look. You don't need to know the details of that, but I think it's interesting that you actually see what the d electrons look like. Okay? So you have dxy, where they are localized about the xy plane, dyz, where they are sort of orientated in the xz plane, and this one here, which is quite different to the others, is the dz squared one. So for the f orbitals, or the f states, this is what they look like. They exhibit more different lobes, okay, and they are quite complicated in structure. So this is what the electrons are doing. This is where they are living in these orbitals here. Okay, so as I said, we're going to look at isolated atoms first, and then we're going to build the solid later on. So what are the 3 sources of magnetism in your atom? You have the spin of the electron. The spin can be up or down, that is +1/2 or -1/2. There is also magnetism due to the electron orbital motion around the nucleus. Okay? And then there is the change in this orbital motion if it's induced by a magnetic field that's applied to the atom. As I said before, if you can think of it classically, you can actually derive some of these equations classically and quantum mechanically. As we'll do that for dimagnetism, you can see that you can derive the same expression. So for the orbital motion, as I said before, you can think of the electron acting like a current around the nucleus. It'll produce a magnetic field and will generate a magnetic field, these rotating electrons, in the direction opposite to the applied magnetic field, according to Lenz's law. Okay? And we label these states with the quantum numbers NL, M, subscript L, and MS. Now this can be a bit confusing depending on which field you come from. Sometimes, like this is the principal quantum number, this is the angular quantum number, this is the Z component of the angular momentum, L representing angular momentum, and this is the spin of the atom, okay, or the electron. So sometimes you'll see, it's usually NL, NL. Sometimes you'll see it written as M subscript L, and sometimes you'll see it written as M subscript S. Other times you may see it written as L subscript Z to indicate the Z component of that angular momentum vector, and sometimes the spin will be written as a sigma z. So we start with considering Hund's rules. Who knows about Hund's rules? I bet the people who have done chemistry probably are well aware of Hund's rules, but normally in physics we haven't done them, I think. There's 3 of them, so let's just go over them. Basically, they are rules which tell us how to fill the atomic electronic states given a certain number of electrons. Okay? Some of the shells in the atoms will be completely filled, so we don't need to consider those. We are considering how to fill the electronic states of the electrons that are in unfilled shells. Okay? So here we have these 4 quantum numbers that I mentioned, n being the quantum principal quantum number, n goes from integer numbers 1 to up to whatever. Angular momentum is L, and for example, we'll get that to the next. These are also integers, 0. It starts at 0 and then goes 1 to whatever, up to n minus 1. Now, this is the z component of angular momentum, and for a given L, say if L is equal to 1, then Lz can vary between minus L up to positive L. We'll do an example of this later on. And the spin, as I mentioned before, can just have positive half or negative a half. Now, sometimes, another bit of notation here, sometimes these angular momentum shells, the L equals 0, 1, 2, 3. In other fields, they are just called, or they are known as S, P, D, and F. Okay? So the S orbital of an electron in an atom, you know, that's just the spherical one. That corresponds to L equals 0. The P state, which has the three P states, that corresponds to L equals 1, and so on. D is known as L equals 2, 3 is known as F electrons. And remember, as we saw before, the S shell can hold 2 electrons, and the P shell can hold 6. Remember, it's got the 3 lobes, but it can accommodate 2 electrons, spin up and spin down. The D has 5 of those lobes. Remember, we saw the D has 5 of the lobes. Each of those lobes you can have a spin up and spin down, so it can hold 10 electrons, and so on. Okay. So just to give a visual idea what these LZs are, you have a given L, angular momentum. In this case, it's 2. And so the LZ can vary from minus 2 up to 2 because it corresponds to vector rotating around the applied magnetic field direction sort of indicated here. So I put that there just to give you, a picture says 1,000 words, and it sort of helps to visualize what these L's and LZs look like or how they are thought about. Okay, so let's talk about Hund's rules. The 0th rule, okay, we start filling, so you've got your atom, you've got various states, you've got high, or the most strongest bound electrons in the lowest orbital, and the more weakly bound, the valence electrons go into these higher states here. So how do we actually fill them? Well, Hund's first rule says that we start filling the shells with the lowest available energy state. That is like at number 1, and that's the strongest bound electron to the nucleus. Okay, so we start filling the states from the lowest one, which is number 1. Okay, and this is a sketch of how you can think about filling the shells. So let's do an example. If you've got nitrogen, you know that it's got 7 electrons, okay? So this is its electronic configuration for nitrogen. It's a fairly light atom. So it's in the 1s state, it's got 2 electrons, spin up and spin down. And then next, okay, here's a 1s. Then we've got to fill, we've got 7 electrons. So we start filling this shell here, the 1s, with 2 electrons. And then we go to the next shell. You've got another 2s, which can hold 2 more states. So we put 2 electrons in there, 2 electrons in here. We've got 3 more to go from the p electrons. So 1s, 2s. We go back up to this shell, in the next row, and we have to fill up this state here, 2p. And so we put the 3 electrons into there. We know it can hold 6, but we've only got 3 left over from the 7 that we had, and so on. So I put this green line to sort of indicate 1, 2, 3, 4, 5. This is the way we start filling. 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, and so on. Okay. This is called the Madelung rule. I think in different countries it's got various names. So an example here for this praseodymium atom, it's got very many electrons. It's got 59. So if you follow this filling rule, you will end up with this electronic configuration given down here. Okay? So you can verify that yourself, that this ordering kind of follows this picture that we have for filling the orbitals. I must say that there are some atoms that don't precisely follow this ordering, so there are some exceptions to this filling rule. As you probably know by now, sometimes we don't want to write down this big horrible sequence of electronic orbitals. Usually we put in brackets the atom sort of at the far right of the periodic table, for example, xenon, and just give the last 2 of the valence kind of shells. So that's the 0th rule, if you like. So, okay, we know to start filling them that way. So what else do we need to do? So we have to start, you see, each electron's got its spin, okay? We've got these various states that can go in. So we have to put the electrons into the orbitals in a way that the spins are aligned, okay? Not like that, like this. So that's the first rule. It says that electrons try to align their spins so that the electron should occupy the orbitals that maximize the total spin. Okay? If I've got 2 electrons with spin up, I've got a half plus a half. The total spin is 1. Okay? So let's just have a look at this atom here, praseodymium again. We've got 2 s electrons in the outer shell, and we've got 3 f electrons. This is filled, the s shell, so we don't need to worry about that. We have got 3 valence electrons in this unfilled f state, and so we need to decide how they should be with their spin. So we know that we need to put them with their spins aligned, so we get half plus a half plus a half, and that's the way we get the total spin of 3/2. Okay, what's the next rule? Okay, so we know how to put the spins. The next rule says that we need to occupy the orbitals such that we maximize L, big L. Now, big L is equal to the sum of those LZs. Okay, so let's think about it. So we know that for praseodymium, it was our F shell that is partially filled. So we're dealing with an F shell. Remember the F corresponded to L equals 3 from the previous slide. So we know that for the F shell, the possible values of Lz go from minus L up to plus L. So we have 2L plus 1 states that we can possibly put these aligned spins into. Now this rule says that we have to maximize L. So we're going to start filling with the biggest number. Okay, so we put 1 electron in this state, next biggest, and next biggest. So in this way we have maximized the sum of the LZs, and that is equal to 6. 3 plus 2 plus 1 is 6. Okay, so we know to put the electrons into those states. And if we need to calculate now the total angular momentum, we have 3 kind of questions that we need to consider. This is called like the subshell, or the F shell if you like, and when it is less than half filled, which it is in this case, we calculate J to be equal to L minus S. So in our case we had L was equal to 6 minus the spin, which we had was 3 over 2. So the calculated J, total angular momentum in this case, works out to be 9 over 2. Okay, so I just want to go a bit aside and consider, why do the spins like to be aligned? Why do they not prefer to be anti-aligned? This sort of gives you a picture to understand that. It's a fairly simple picture. But for example here, when the spins are here aligned, the Pauli repulsion keeps those 2 electrons far apart. So they're repelled from each other, okay, these 2 electrons. And when they are further apart than in the opposite case, it means that there is a greater Coulomb interaction between that electron and the positive nucleus. In this case, when they're anti-aligned, they can get closer together. And for example, this electron then, the interaction with the nucleus is reduced due to the negative charge of this electron. So we say that this electron is partially screened by the closeness of this electron. Okay. So let's just do an example together. I just want to make sure you get this. So if we consider chromium 3+, so you're given that, and we have to, work out the values of L and J. How do we think about it? Well, we can first look at its electronic configuration. Okay, so we go to the periodic table or wherever you go, and you know that it's equal to argon, 3d5, 4s1. But that's for chromium, but you're given chromium 3+. So that plus means it's given away 3 of its electrons. Okay? So it will give away this electron, the weakest bond from the S state, and it will give away 2 of these D electrons, so it'll only have 3. Okay? So what you're dealing with is just 3 electrons in the D state. That's the first thing to realize. So due to Hund number 1, we align the spins so that S will equal, we put them parallel to each other, so we get a half, a half, a half, equals 3 over 2. And then due to Hund 2, we know that chromium, we're dealing with a D state, and this corresponds to L equals to 2 from what we learnt before. So it means that the LZ can go from -2, -1, 0, 1, and 2. Okay, and we know that we have to maximize L. Big L equals the sum over the small l. We need that to be maximum. So we put the electrons in the 2, 1, and 0. So big L will then equal to 0 plus 1 plus 2 equals 3. Okay, and then when we look at our occupying these shells, we see that we are less than half filled. Well, L equals 3. So we calculate J according to L minus S. 3 minus 3 over 2 equals 3 over 2. Okay, I think that's kind of straightforward. Okay, so let's just look at some other kinds of terminology in this area. That's what we just did. A bit more detail than is done there. Sometimes when you look at spectroscopy results, yeah.
I just wanted to last example, use the J equals L minus S because we're in such a less than half full. Does it have 3 electrons in it?
Yes, it has. That's a good point. Let's look again at if the subshell is more than half full. If the shell is half full and J equals L equals 0, well, L doesn't equal 0, and J equals S. Yeah, the thing is, the subshell is, yeah, the thing is it's still less than half filled, you see, because let's just go slowly. If the shell is less than half filled, we use that. If the shell is, so you're concerned about this one. If the shell is half full, L equals 0. The shell is half full. Let's just think. It can, yes. Yes, yeah, because you can put some up and some down. Yeah, that's it. Very good. Did everybody get that? So you can put them, I just go back to the picture that I had because I think that's a very good point. Our picture here, right, 1, 2, 3, 4, 5, it's half filled, yeah, because say if you had to fill it up with 8 electrons, then you've got 5 and then 6, 7, 8. Each state can have an up and a down, okay? So even if so the maximum is 10 that it can have, and we were just filling 3. So even though it looked like 3 out of 5 was bigger than half, you've got to compare it to 10. Okay, so this is, if you're looking at some kind of spectroscopy results, they use a different notation again. So they label according to this hallowed spectroscopic code. Okay, so this here, L, corresponds to our total LZ. Okay, this big L here. And the X that they use, in their notation here is such that if the total of the Z component of the angular momentum is equal to 0, we use an S. If it's equal to 1, we call it a P, If it's equal to 2, we call it a D, and so on from this table here. And then you label it such that that was the X that you get from here after calculating the total L. And then the lower subscript is equal to J that you will calculate. And then up in the left-hand corner of the X, the superscript there, you have 2s plus 1. So what I've put here is just one example that we can consider. So let's go through it. This is vanadium. Okay, these elements correspond to these numbers here. So the vanadium has 3 electrons in its D band. We are just considering the D shell, and we know that it has 5 states or orbitals, and each one of those can hold 2 electrons. So we are dealing with 3 D electrons. So according to Hund, the D states can go from minus L, doesn't matter which way you write it, up to plus L. So, and then we have to fill them in the parallel way. Okay, so then you can calculate the S, which is the sum of a half plus a half plus a half. And then you can calculate the sum of the Z component of the L. So you've got this one here, which is 2 plus 1 is 3. So you get the 3 there. And then again, the J is calculated as L minus S here. So we have 3 minus 3 over 2, which gets you the J, which you can see down here. Okay? And we see that the F arises due to the fact that our sum of the Z component of the angular momentum is 3. So 3, we get the F. Okay? And then up here, the 4 comes just 2 times the spin. This is the spin. 2 times that's just 3. And then plus the 1 gets you 4. Okay, so if you see these kind of notation in the literature, you'll know how they are obtained. And this is from Ashcroft and Merman, as I've put down the bottom there, if you want to read on a bit more about that. You can do the same thing for the F electrons. In this case, we can look at samarium, and it has 6 electrons in its F shell. You can sum up the spins, just 6 times a half gets you 3, and just add up the sum of these L's. Some negative ones will cancel out with these positive ones, and you just get the 3 over here. And then you can figure out that J is going to be 0 in this case, and then you can get J down here, and the same thing up there for the 2s plus 1 notation up there. Okay, so we've got our atoms. That's the way we fill up the shells. Now we're going to put that in a magnetic field. So what we're going to do is replace the momentum operator with being equal to the momentum and this vector potential term. Okay, maybe you're familiar with that from your electromagnetism course. So, you know, when we don't have the effect of a magnetic field, this is our usual Hamiltonian. Okay, this is the potential that the electrons see from the nuclei of the atoms, and this is the kinetic energy. So now it's in a magnetic field. We've had to replace the momentum operator by P plus E times A, where A is this vector potential, and you get this, but you also get this additional term, which is called the Zeeman term, which I'll show you in a second. But this is sigma, so this is the spin of the electron. And this G is called the G factor. It's derived in great detail in the textbooks, but you don't need to know how to derive it here. It has a value of about 2, and mu B is the usual Bohr magneton. Okay, we have h bar E over 2 times the mass of the electron. So this Zeeman term is due to the Zeeman effect. Who's familiar with that? All of you? None of you? Some of you? Some of you, yeah. So, for example, over here you've got an angular momentum of 1. So this is a p kind of state in your atom. And then up there you've got a d kind of electron, L equals 2, happily sitting there. And then you turn on this magnetic field, and what happens is you get a splitting of these levels into the various LZ that they are allowed to have. Remember, so these are the LZs, if you like to think of it. For L equals to 1, remember we saw it could take the values -1 up to +1. So you get a small splitting of these levels, and the splitting is just equal to E h bar over 2m, okay, the Bohr magneton. So the D state correspondingly splits into its 5 discrete levels. And so that, when you're doing spectroscopy of these atoms in a magnetic field, you will detect various transitions from all of these different possible combinations. Okay, so this was first proposed or predicted by Lorentz, and it was first experimentally observed by Zeeman, hence the name of the effect. Okay, so let's go on a little bit more. Okay, so remember from the previous slide, we had the expression for the Hamiltonian. In the presence of a magnetic field, we had the new term arising here, this Zeeman term, and we had the momentum going to momentum plus E vector potential A up here. So basically, when you expand this square up here, you will get this expression here. So this is obtained just by undoing that squared term. So 1, 2, 3. Then what you can do is rewrite this third term here, B dot cross product of B times R. You can rewrite that just in another way as being B dot product R cross P. And when you do that, you can recognize that this R cross P term is just the angular momentum of the electron. So you have replaced the R cross P just by L, the angular momentum, and the H bar has been folded into here, so that this prefactor turns out to be just equal to the Bohr magneton, this expression here. Okay? So that follows quite reasonably. And then, so we had rewritten the third term as this on the previous slide, mu B magnetic field dot angular momentum. So we had this expression before. This is exactly what we had on the previous slide. And when you look at this term here, okay, you've got B dot spin. Here you've got B dot angular momentum. You can just pull those two terms together and get this expression here, B dot angular momentum plus that G thingy factor plus the spin to obtain the final expression. Okay, so this is the final expression. Okay, so when we look at this expression for an atom in a magnetic field, the paramagnetic term is this term here. Remember, the paramagnetic term was due to the spins that exist in the atom becoming aligned to the magnetic field. So that second term is the paramagnetic term, and the other term is the diamagnetic term. Now, every atom exhibits a diamagnetic term, but it's usually extremely small and you don't really notice it. And so these two terms are the ones that are responsible for paramagnetic and diamagnetic responses to atoms in magnetic fields. So this is important equation here. Okay, so what we're going to do next is just look at each of these terms in a little bit more detail. We'll first consider this paramagnetic term. And so that's written down here. Okay. You can show, it can be shown, and I'm not going to show it, but you can rewrite the Hamiltonian as being equal to B dot product with the total angular momentum J. Okay, and you've got a little twiddle on this G now, and that's because this G has taken this expression here. It's derived in the textbook, and it's also derived in the Ashcroft and Mermin appendix. You can see what it looks like. You don't need to know how to derive it, but that's the form that it has. So the partition function here is obtained by summing up all of the j from minus j to plus j, e to the beta, which is usually 1 over kBt, okay, and then our term here. And the free energy, as usual, takes the form minus kBt log of the partition function. Now, why are we doing that? We are doing that because we want to get an expression for the magnetization in terms of the magnetic field. And when we have that, we can differentiate it and we'll get an expression for the susceptibility, which is what we are after. We are after an expression for the susceptibility for the paramagnetic term, and we'll do one for the diamagnetic term. So the magnetic moment per spin, as I mentioned before, you can, if you differentiate the free energy as a function of the magnetic moment, that will get you the magnetization per spin, and from that you can get the susceptibility, because remember we had on the very first slide when we had those fundamental equations, the magnetization was equal to the susceptibility times the magnetic field divided by or multiplied by mu b. Okay, so you can go back to that original slide and basically, yeah, see why this comes out. Actually, I thought I wrote it down for you. Anyway, doesn't matter. So basically, you are differentiating the free energy with respect to the magnetic field. You get the magnetization. Once you get the magnetization, you know that magnetization is equal to the susceptibility times the magnetic field, either divided by or multiplied by mu b. And so that you can extract here the susceptibility from it. Okay, now so this is important because you can lump all of this coefficient into one constant called C, and that's called the Curie constant. So what does it say? It says that when you've got a paramagnetic material, okay, you've got it in a magnetic field, as a function of temperature, the higher the temperature, the lower the susceptibility will be. So this is a very famous law, and sometimes it's modified into the Curie-Weiss law, where you've got an expression involving also the critical temperature, because you know at a certain temperature you will lose, you'll be a ferromagnetic. You can also apply it to ferromagnetic systems, and at a critical temperature you will lose that ferromagnetic ordering, and this kind of modified Curie law turns into a Curie-Weiss law, which is applicable to ferromagnets. But at the moment, we are just dealing with not ferromagnets. Okay? We've just got single atoms in a magnetic field. Okay, so this is important. Let me see how I'm going for time. I probably may have to stop here, or maybe I'll just finish this section here. Basically, what we do now is we go back to that equation, and we now look at the other term, the diamagnetic term. Okay, and remember, it was written like this here. This is just from the previous equation, and what is being done is here we are just solving or breaking this expression down, assuming the magnetic field's in the z direction, and replacing this term basically with 2/3 over r squared, where r is just, we're assuming a spherically rotationally symmetric atom. Okay, so we've got the r vector, we've got x and y directions, and so this is, why we get this 2/3 of r from our x squared plus y squared. Because x squared plus y squared plus z squared is r, but we've only got x squared plus y squared, so we've only got 2/3 of r squared. Okay, so this is the last slide that I will, I think, show for today. Basically, okay, this is what we had before. We are now putting that 2/3 r, and we are differentiating again the energy with respect to magnetic field to get the magnetic moment. And we are recognizing that when you do that, that magnetization or the magnetic moment is equal to the susceptibility times the magnetic field divided by μ0. You can put these two over the other side and solve for the susceptibility. And when you do that, you get this expression here. Okay. So I'm not, probably I should put a red box around that one. That would be good. You can put a red box around this susceptibility, and probably also, okay, I have one already for that. Yeah. Okay, I think we'll leave it here and carry on next week with a bit more magnetism. Again, anybody got any questions for this assignment, just email me. Happy to answer any questions. Has anybody had any trouble uploading assignment yet? Or you? Yeah, you can come in. We've finished. Okay, anyway,